Hello and welcome to this tutorial. Today we're going to look at a direct influence analysis and a moving load analysis on a skewed plate girder bridge. The bridge in question is this one. There is another video which is similar to this one, but here we're not going to run a fatigue analysis, so we will let the truck free to change locations transversely across the bridge. So again, this is a composite analysis as the deck is modeled explicitly and acting fully compositely with the steel superstructure. I am going to go really quickly over the geometry as we've seen this bridge before. This is the deck elevation, which is the distance between the bottom of the bottom flange at the midplane of the deck. Here are the material properties. I am using the full modulus of elasticity for the concrete as we're applying live loads. Here are the stiffeners. Here are the cross frames which are attached onto the stiffeners. You can see that I have zeros when I have lean-on braces such as the bottom and top chords, and then 1 when I have full cross frames. I am meshing the deck in just one go. This is why I have just one segment for the deck. This is because it's a simple bridge. In case of a more complex system, you would apply more segments in order to help the mesher properly mesh the concrete deck. I have 5 fixity in terms of boundary conditions here. I have the first abutment here at girder number 1. It's fully restrained here at node number 2. And then we have transverse restraint at the other end, and for the other girders we just have a vertical restraint at the bottom flange node. This is to allow the bridge to really breathe. I won't click on this button as the model is already run, but again, if you ever change the reference points, you will need to click on this button. This is for the program to properly apply nodes, define nodes wherever you have reference points. Here is the mesh size. Here is the cross-sectional profile. We are, of course, assigning this profile number 1 to all the segments. And here are the influence surfaces that we want to have on the bridge here. We will look first at girder line number 2. Location along the girder will be 0 at the bottom flange, and desired quantity 10 is the vertical reaction. So we are looking to get the influence surface for the vertical reaction at abutment 1 on girder number 2. Then influence surface number 2 will be at girder line number 3. Location along the girder is this. So let's see what this really means here. Let's check if we have a cross frame or something else. This is here. Yeah, this is this cross frame here, which is about at mid-span of the girder. Okay, these points can't be selected. These locations can't be selected at random. You need to have a node there, which is why we are selecting here one of the reference points, in this case 58.7. And here the desired quantity is 3, which stands for UZ. So we're looking at the influence surface for the vertical displacement at a mid-span of girder number 3. And the location on the cross-section will be 5, which really here is the center node of the cross-section. The third influence surface will be again at girder line number 3 at the same location, and we're looking at quantity number 15, which is the composite moment. So that means the steel structure together with the concrete deck acting compositely. This is the form for the moving load analysis. We have one truck model. That truck model has 3 axles. The distance between the wheels is taken equal to 6 feet. This is the standard AASHTO truck. We also have a design lane load of magnitude 0.64 kip per foot. The increment in the longitudinal direction for the truckloads will be 1 foot, and in the transverse direction we will consider 7 positions. We have 3 design lanes. You can see the design lane width will be taken equal to 10 feet. In this column, we are specifying the distance between the center line of the design lane and the edge of the deck on the left side of the deck. So here it will be 8 feet, which means that the leftmost point on the design lane would be at 3 feet from the edge of the deck. The next design lane would be located 10 feet further to the right. Okay, that's absolutely logical as they are all 10 feet wide. And here are the multiple presence factors. Okay, the solver here, the subroutine, will calculate all types of configurations, whether one lane is loaded, whether 2 lanes are loaded, and apply the relevant multiple presence factors together with the dynamic load allowance here, which is taken as 1.33. And finally, this table says that, yeah, for these 3 influence surfaces, we will conduct a live load analysis, meaning we will try to find the critical vehicle load locations which maximize and minimize the effort, whether here a reaction, whether a displacement, or whether composite moment. If you have any doubt on any parameter here, we've tried to make this form as easy as possible, but of course it can't be a piece of cake either, as this is quite an advanced analysis. We have this help button here which goes through each of the parameters. In any case, feel also free to send an email if you have any doubt. This is following AASHTO, but of course we are making this open in order to comply with any other code, any other design code. The model is run, so I won't click on the Run button. I will instead just go to Viewer. The running time was about 10 to 12 minutes, actually slightly less, probably 8 minutes. So now let's just go to the model. We can see here that it's pretty simple system, just simply supported. Let's go to influence surface number 1, which again is about the vertical reaction at this node here. As expected, the maximum value is obtained when the load is applied right on top of the girder here at abutment 1. Something that I think is interesting is that we are nonetheless capturing possible uplifts when the load were to be applied here at this tip or at midspan on bay number 3. Of course, this is as expected, but it gives us confidence in this influence surface. And if the load were to be applied directly on top of the girder here of the abutment, the reaction would be very close to 1. So again, this is as expected. This is 0.98. Now, if we click on this button, we will see the critical vehicle configuration for that influence surface. This view is a bit confusing, so let's go instead to the top view. Let's increase the size of the loads. And we can see now where's the critical truck. We have actually 2 trucks side by side. One is here and the other one is there. You can see 6 point loads here and 6 point loads there. So here the multiple presence factor would be 1. And of course, because the influence surface is positive here on these 2 design lanes, the whole length here is also loaded. So here the maximum reaction would be 136 kips. Let's now go to influence surface number 2, which is about the displacement, so UZ at cross-section node number 5, so that's the center node on the cross-section. at girder 3 at y equals 59 feet from the abutment. As expected, this is negative. The bridge is simply supported, so any load applied on the deck will lead to a negative displacement on that node. If we click on that button again, we will see that the critical vehicle configuration to maximize the vertical displacement at that node is obtained when we have 3 lanes loaded. So here the multiple presence factor would be 0.85, and of course we have a point load here that's very close to the minimum of the influence surface. The other on the design lane adjacent to that other lane, we can see here that we have the truck located right here, and finally for the third design lane it's right there. So overall we have 6 times 3 equals 18 point loads, and the maximum displacement, well, I should say the minimum displacement would be about 2.1 inch. Now finally, for the composite moment there, this is the influence surface with a pretty high concentration here. Let's click on the button again to look at where would be the load for the maximum value. This is the minimum value. This is the maximum value. It is a bit confusing here because, of course, this is all positive. So what we need to do here is enter a 0. And now we can see it. Let's go back to the top view, and we can clearly see where it is. We have, of course, a point load as expected. This makes total sense. Okay, we have a point load right at that concentration, and this would be the truck on this design lane. And then again, we would have 3 design lanes loaded. Here would be the truck in the design lane to the left here, and then the truck on the design lane to the right. And the maximum moment in this case would be about 32,000 Gibbs inch. So I hope this is useful, even though the bridge considered is pretty simple. But again, this is quite useful to have a shell model because we can capture transverse effects instead of just doing a wind load analysis with distribution factors. Thank you very much.